We're going to tie in kinetic molecular theory. I don't know if you remember last year we were talking about it with thermodynamics. So um, hopefully you'll remember some of the things that we talked about in this section. Okay, so we are assuming that gases, typically they are molecules, but you could have maybe a noble gas where it is essentially an atom by itself, and they exert kinetic movement, and we measure that movement as temperature. We look at the average of that kinetic movement. We're assuming that these gases, they typically move in straight lines. Their movement is random. They collide with each other. They also collide with the container. Now, we're assuming that they take up very little space. I don't know if you've heard me explain with gases, it's like having your relatives that cannot stand each other in the same room. They're going to occupy the furthest corners of that space. And gases are doing that themselves, where they're trying to stretch out as much as they can with the space that they're occupying. And the bizarre thing is that we can use this. We assume that the volume of the gas is actually zero, which is bizarre, but it works. So we're assuming that these gases occupy almost no space, and as a result of it, it works really well with ideal gas law. Now, the interesting thing with gas is we just got done talking about intermolecular forces. We're assuming that the force of attraction is non existent or repulsion is non existent. So when these gases collide with each other, they're not attracted to each other, they actually bounce off of each other. And there's no force of repulsion that's driving them away from each other. They just naturally collide and then bounce off of each other or the container. So, what does this mean? This means that kinetic energy is conserved. So, if they collide with the wall, we're assuming that the initial kinetic energy that they had before they hit the wall is going to be the same after they hit the wall. So, we're assuming they do not lose energy when they collide. Now, we could have a transferring of energy when they collide with each other. So you may notice that one particle starts off with a higher kinetic energy, but then after the collision, it transfers that kinetic energy to another gas particle. So we can say that the average kinetic energy is a good measurement of the movement within that gas. So we're assuming that whatever the temperature is, that is the proportional energy for that gas in that container. Now, how does a particle within the gas move? We assume, like I said, they move in straight lines. They could be spinning or have rotational energy while they are moving. We're also assuming that they vibrate or they kind of shimmy back and forth as a part of that movement. Now, you would argue that most of the energy is taking place in the movement of straight lines. Okay, so this graph should look very familiar. Notice that on the y-axis, we're looking at the number of particles. So we're looking at how many particles share that peak with that specific curve. And notice that we're looking at kinetic energy or the average temperature. So notice that we're keeping volume the same. We're just looking at temperature and pressure. And notice at 250, we have a large amount of particles that are at a lower temperature. So if you were to like dissect this curve, you would see the majority of these particles are at a lower temperature. We have some that are even extremely cold, and we also have some that are warmer, but the majority of them are at this lower temperature. And notice with the next curve, as you go up in temperature, we see a widening of the curve. So we have a different spread of particles as we see that temperature changing. And then obviously, if you have an even higher temperature, we have a spreading out of the different types of temperatures for that set of particles. So you could argue that with this green curve, the majority of the particles, they're spread out a wider range of temperatures. So the average kinetic energy of a gas actually increases. So we have a larger range of kinetic energy. So at that 1000 Kelvin, we have a wider range of particles that are at different temperatures. Whereas the cooler the gas is, we have a larger percentage that are at a lower temperature, but we also have a smaller percentage of particles that are at an extremely low temperature or at extremely high temperature for that curve. And you can argue that the total pressure of that gas is also at an average. Okay, so once again, we're going to tie in with kinetic energy, and notice that we're looking at velocity and mass. And what I typically tell my students is if you have a baseball and a basketball, you want to think about which one is harder to throw. And gases kind of behave that way. Obviously, the smaller the mass, the faster the gas. The larger the mass, the slower the gas. So here is an example of 3 different gases. Notice that we have oxygen, and notice it's not 16 because it's O2. You got to pay attention to that. Same with hydrogen. There are 2 hydrogen atoms bonded together, so don't say that it's 1 AMU. But notice how oxygen, because it's a larger mass, it's slower. So as a result of it, its average speed is slower. And there's a large number of them that are at that slower speed. Whereas helium is obviously a significantly smaller gas. Notice that its average speed is significantly higher. And it also has a wider range of speeds because of that. And the key piece you want to note here is here they're holding temperature constant. So we're just looking at the different molar masses, and we're looking at the amounts of those gases at that specific speed. Now lastly, hydrogen, we have the widest range of speeds for that gas. And obviously we don't have a sharp number at a specific speed. It's kind of spread out at a large range. So we have some small percentages that are under 500 meters per second. Obviously, the average is centering around 18, maybe 19, depending on your perspective. And then you have a smaller amount of hydrogen that is 3,000 meters per second. So obviously the smaller mass gas has a wider range of speeds, and we don't have a sharp or a very high percentage for a specific speed. Now, for a given temperature, the average kinetic energy should be the same. So in order for ideal gas law to work, it doesn't matter about the identity of the gas. It does matter about the specific temperature. We could argue, though, for gases with smaller molar masses, they are going to have a higher average velocity. So their center of their curve is going to be higher because they are a smaller mass. Whereas gases with larger molar mass, they are going to have a lower average velocity. So it's going back to the baseball basketball argument. Oxygen is a larger mass, so as a result of it, it's going to have a lower average velocity, and its peak is going to be a sharper peak. So there's going to be less of a wide spread with the different molecular speeds.